Okay, what else? You guys are doing good. Is this helping? Or would it be better to walk through each mechanism?
This is helping.
Okay.
I have a halohydrin.
Okay. And what is a halohydrin?
That's the same thing but with water.
Okay, good. So how do you know where the water's going to add versus the bromine? Which one's going to be in the more or less substituted position?
I want to say the water's going to be the most substituted position.
Okay.
But I don't remember why.
You don't remember why? Okay. Maybe.
Is it because the hydrogen want to be with its friends?
Yeah. We can draw it up here. The mechanism is just really small. Okay, so what are your reagents? What do you have to add?
Br2 with water.
Okay.
Or Cl2 with water.
Okay. So okay. And on your mechanism chart, is it showing the pi bond reaching out and grabbing a bromine, or is it showing it reaching out and grabbing a water?
Bromine.
Bromine. Okay, good. So the pi bond reaches out, grabs a bromine, and this first little bit is similar to this, right?
Yep.
And the bromine's going to break it bond to its partner bromine. Where's the bromine going to go?
Is it in between the two? Like a little triangle?
Di substituted.
You're saying it would be here? Well, okay, if we put it here,
You have a
we'd have a
carbocation.
carbocation there, right? If we put it here,
You have a carbocation. So it's like between the two of them, right? It's like a little triangle thing underneath or above. Or am I thinking of the wrong mechanism? Yeah, it makes like a little triangle thing.
I might have totally messed up. What page is this on?
Section 6.14.
253.
253. You're right. I'm sorry. I don't know why I was thinking it was breaking. Yeah, okay. Well, I mean, it does break, but it doesn't. Okay. Start over. Okay, so it reaches out, grabs the bromine. The bromine is then in this little three-membered ring, right? We have the part. Okay.
Yep.
It's going to have a positive charge as well. Because if you go through and look at the formal charge, it's going to end up positive since it has more bonds than it would like. Okay, and then, so in this one, this bromine came in and did the backside attack, broke the ring open, and you're left with a vicinal dihalide. In this case, water is going to come in and do the backside attack. And so which carbon is it going to attack, this one or that one?
Most substituted.
The most substituted, and why?
Because that's most stable.
It is. You're not going to form a carbocation in this mechanism, but as you're breaking the bond, one of them is going to have carbocation-like character, right? So if you broke this bond, you'd have a primary carbocation-like carbon. If you broke that one, it would be a secondary carbocation. Like, it's not a full-fledged carbocation, but it does become partially positive as this bond is breaking and that bond's forming. So we'll go to the most substituted one. Break the bond up towards the bromine, and we'll be left with an alcohol on the most substituted carbon. Well, I guess
Water.
we've got water, and then what happens? Sorry, I forgot that.
Then another water comes in and plugs the hydrogen.
Good.
Now, does the alcohol and the bromine have to be anti to each other?
They do. Yes, and why?
Because it adds from the other side,
Yeah, good.
bottom.
Good, because in this step, this came from the back and broke that bond from the back side. So we can, and then again, in this case, it's like, it's spinning around those sigma bonds, and to define what's towards you and what's away isn't really important. But if this was a ring and it had a locked configuration, then it would matter to remember that it does add anti. So we'll draw it again. Okay, does that make sense?